In the previous lecture, we were looking at the stress tensor. Okay. So, basically if I have a fluid which is flowing, okay, okay, and I look at some velocity field, okay, and the fluid flows because the momentum is being transported across the flow. Okay. So, if I have some surface here, okay, okay, the fluid on one side of the surface is exerting a force on the fluid on the other side, okay, and these have to be equal and opposite forces, okay, that are exerted by the fluid on one side of the surface with the fluid on the other side. Okay. Okay. So, if I look at the surface itself, okay, so I will just draw the surface here for simplicity. Okay. And if I consider this surface separates two volumes, one is above the surface, the other is below the surface. Okay. So, the unit normal to the volume below the surface is upwards, okay, and the unit normal to the volume above the surface is in the downward direction, okay, and the forces have to be in opposite directions. Okay. So, okay. And the forces have to be in opposite directions. Okay. So, if the volume above is exerting a force like this on the volume below, there has to be an equal and opposite force acting on the volume below. Okay. And this implies that the force acting at a surface can be written as a second order tensor times the unit normal. Okay. This second order tensor is the stress tensor, okay, and I defined it for you formally in the previous lecture. Sigma ij is the force per area in the I direction acting at a surface with outward unit normal in the j direction. Okay. So, therefore, sigma xx, so the for example, if I take a Cartesian coordinate system, sigma xx is the force per unit area in the x direction acting at a surface whose outward unit normal is in the x direction. Okay. Okay. So, if this is x, y and z, okay, the surface with outward unit normal in the x direction will be in the yz plane. Okay. It will have an outward unit normal in the x direction in the yz plane. Okay. And the force per unit area acting at this surface is defined as sigma xx. Okay. Okay. So, the force per unit area in x direction acting at surface with outward unit normal in x direction. Okay. So, that is the component sigma xx. Okay. Similarly, sigma xy is the force per unit area in the x direction acting at a surface whose outward unit normal is in the y direction, and so on. Okay. So, the total force, so at a given point in space, okay, the force exerted depends upon the orientation of the surface. However, the stress is independent of the orientation of the surface. It is defined uniquely at each point in space, such that the stress dotted with the unit normal gives you the force exerted, okay, at that particular surface. This is analogous to the relation between the mass transported per unit area and the mass flux. Mass flux is a vector that is uniquely defined at each point in space. The mass transported per unit area per unit time across a surface does depend upon the orientation of the surface. Okay. So, the mass flux is something that is uniquely defined at each point in space. Okay. The actual mass transported per unit area will depend upon the orientation of the surface and the unit normal. Okay. So, it will be different in this case as opposed to, for example, if you had a surface whose unit normal was in this direction. Okay. And that mass transported per unit area per unit time is equal to j dotted with the unit normal across the surface. In a similar manner, the stress tensor, okay, which I had written for you as Ex, Ey, Ez, okay. This is a uniquely defined at each point in space. Okay. The force exerting at a exerted on a surface, okay. So, the force that is exerted on the surface, okay, depends upon the orientation of the surface or the unit normal to the surface. Okay. The force exerted at a surface, okay, is going to be equal to this sigma dot n times the surface area itself. Just as the mass transported per unit time depends is equal to the flux dotted with the unit normal times the area. Okay, the mass transported per unit time is proportional to the surface area. Okay. Similarly, the force is also proportional to the surface area. It is equal to the sigma dot n times delta s. What are we doing when we write sigma dot n? That means that, recall that I told you that this is the direction of momentum, okay, or force, okay, and this thing is the direction of the outward unit normal. Okay. So, if I dot the second index with the unit normal, I will get the force exerted. Okay. Okay. So, therefore, this is equal to, for example, if I have the unit normal as Nx Ex plus Ny Ey plus Nz Ez, okay, then what I am doing is I am dotting the second index here with the unit normal, okay, and once I do that I will get a vector. Okay. So, this is going to be equal to delta s into, okay, first Ex, okay, into sigma xx nx plus sigma xy ny plus sigma xz nz. Okay. So, this Ex here I have dotted with Nx here, Ey with Ny Ey and Ez with Nz Ez, okay, plus Ey into sigma yx Nx plus sigma y and y plus sigma yz and z plus Ez into sigma zx nx plus sigma zy and y plus sigma zz and z. Okay. So, that is going to be the force exerted at a surface whose outward unit normal is n if the components of the stress tensor are sigma xx, sigma xy, sigma xz, etc. Okay. Okay. So, this gives us the direction of the force at a given surface. This does of course depend upon the orientation of the surface. However, the stress itself or the stress components themselves, okay, there are 9 of these, okay, they do not depend upon the orientation of the surface. They are uniquely defined at each point in space, analogous to the flux which is uniquely defined at each point in space, but the transport across a surface depends upon the orientation of the surface. Okay. Note that in this expression, this f that I have got here is a vector because it has only one unit vector. The second one has been dotted with the unit normal. Okay. So, therefore, this is now a vector. The stress is a second order tensor, it has 2 directions associated with it, the direction of the force and the direction of the perpendicular to the surface, the outward unit normal. Now, this force at a surface, I have a surface with some unit normal n, and there is a force acting at the surface. So, this force I had defined as F vector is equal to sigma dotted with n. This can be decomposed into two parts. One is the component along the unit normal, and the other is the component perpendicular to the unit normal, that is in the surface itself. The component along the unit normal is just n dot f, which is basically n dot sigma dot n. This is the component along the perpendicular to the surface, and this is referred to as the normal force at the surface. Now, we know that the tangential force at the surface plus the normal force at the surface has to give you the total force. That is, I require that F plus the normal component of the force. The normal component is along the unit normal, and its magnitude is n dot sigma dot n. This I am sorry, this is the tangential component. So, the tangential component this has to be equal to the total force. Which implies that the tangential component has got to be equal to the total force minus n times n dot sigma dot n, which is basically sigma dot n minus n into n dot sigma dot n, and I have to add the surface area here. This is equal to delta S. So, this whole thing is multiplied by delta S. So, that is how you decompose the force into its tangential and normal components. So, as I said, the stress has 9 components, because it has 2 indices. Each index has 3 values x, y and z. Therefore, the direction of the force can be any one of x, y and z. The direction of the unit normal can be any one of x, y and z, and therefore, you have a total of 9 components. There is an important relation between these components that emerges from angular momentum balance. There is an important relation between these components that emerges from angular momentum balance. So, I will go through that. X and y coordinates, and let us take a differential volume. Let us take a differential volume. I am taking the plane perpendicular to the z direction. So, let us take a differential volume of height delta x in the x direction. So, of length delta x in the x direction and height delta y in the y direction. And let us look at a momentum balance for this. So, at these 4 surfaces perpendicular to the z axis. So, the z axis is in this direction, is perpendicular to the plane. In these 4 directions, let us look at what the stresses are. The normal stress at this surface force per unit area in the x direction acting at a surface whose outward unit normal is in the y direction is sigma xx. Force per unit area in the x direction at a surface whose outward unit normal is in the x direction. Okay. At this surface also there could be a tangential component of the stress. Okay. This is the force per unit area in the y direction acting at a surface with outward unit normal in the x direction. So, this is sigma yx. On the opposite side, okay, the direction of the unit normal changes and therefore, the direction of the force also changes. I told you that at a surface, if plus F is the force acting at a surface with outward unit normal in the plus x direction, minus sigma xx has to be the force acting on a surface with outward unit normal in the minus x direction, because forces have to be equal and opposite at surfaces. So, this is sigma xx at this surface, okay. And similarly sigma yx at this surface is given by this, sorry, sigma yx at this surface is given in the opposite direction. Okay. These are all forces per unit area. Okay. In the y direction you can do a similar calculation. Okay. This is sigma yy. On the opposite surface the unit normal is in the minus y direction, that means that sigma yy is in this direction. Okay. Then this is sigma xy, force in the x direction at a surface with outward unit normal in the y direction. Note that for the surface above the outward unit normal is in the plus y direction, and this is sigma xy at this surface. The force is in the minus x direction and the outward unit normal is in the minus x direction. Okay. So, for this let us calculate the total torque in the z direction acting at this volume. Okay. So, the momentum, the angular momentum balance equation is that the moment of inertia in the z direction times rate of angular velocity change in the z direction, okay, is equal to sum of the torques. Okay. And using the right hand rule, okay, the torque is outward, okay, in the plus z direction, okay, if it is anti-clockwise, and inward if it is clockwise. Okay. Okay. So, basically this is a positive torque, okay, and if it is clockwise it is a negative torque. Okay. Okay, because by the right hand rule the positive torque is out of the board in the plus z direction, negative torque is in the minus z direction. Okay. So, let us look at the contribution to the torques from these four phases. Okay. Contribution from right phase. Okay, is equal to the force times the perpendicular distance. Okay. The force times the perpendicular distance. Okay. So, in the case of sigma xx the torque is 0 because it is normal to the surface. It is only sigma yx at this surface that gives you a torque. Okay. And that torque is equal to the total force, that is sigma yx at x plus delta x by 2. Okay. This is the force per unit area. So, I have to multiply it by the area, and the area is, in this case, is delta y delta z, that is the force multiplied by the perpendicular distance. Perpendicular distance from is this one, okay, that is the perpendicular distance to the force. Okay. So, this is equal to delta x by 2. Okay. So, that is the contribution to the torque from the right phase, okay, and it is in the anti-clockwise direction. Okay, therefore, it is positive. Okay. Contribution from left phase. Okay. Force is minus sigma yx at x minus delta x by 2. Okay. That is this force. Okay. That is this force. Okay. Sigma xx does not contribute because there is the perpendicular distance from the centroid is 0. Okay. So, this multiplied by delta y delta z times the perpendicular distance, which in this case is minus delta x by 2. Okay. That is the perpendicular distance to sigma y x is minus delta x by 2. Okay. Then let us look at the contribution from top face. Okay. In this case, sigma x y is in the acting in the plus x direction. That means that it is acting in the clockwise direction. Okay. Therefore, the torque has to be negative because it is acting in the clockwise direction. Okay. Note that this clockwise direction, the torque is negative. Okay. So, this will be equal to minus sigma x y at y plus delta y by 2, okay, times the area. Area in this case is equal to delta x times delta z, okay, where delta x is this distance, okay, delta x times delta z times the perpendicular distance, that is delta y by 2. Okay. Similarly, you have a contribution from bottom face. So, at the bottom face the force is acting in this direction. Okay. So, that is actually sigma x y at y minus delta y by 2, okay, into area delta x delta z into perpendicular distance is minus delta y by 2. Okay. The perpendicular distance to this is minus delta y by 2. So, these are the 4 contributions. Okay. The moment of inertia about the z axis, okay, for a volume you can calculate that. Okay. So, this basically scales as the density, okay, times integral minus delta z integral by 2 to delta z by 2. Okay. This is basically an integral over the entire volume. Okay. dV, okay, of x prime square plus y prime square, okay, where basically x prime and y prime are the distance to any particular location. Okay. So, the moment of inertia is the distance from the center square integrated over the entire volume. Okay. So, I can write this as rho times integral from minus delta x by 2 to delta x by 2 the volume dx, integral minus delta y by 2 to delta y by 2 dy, and integral minus delta z by 2 to delta z by 2, okay, dz of, okay, x prime square plus y prime square, and I should put primes here because I am integrating over this particular. And this you can easily calculate is 1 over 12 rho into delta x square plus delta y square into delta x delta y delta z. Delta x delta y delta z is the volume times a characteristic distance square, which is delta x square plus delta y square. Okay. So, on the left side, okay, 1 by 12 rho into delta x square plus delta y square into delta x delta y delta z, okay, that is equal to the sum of the torques. Okay. So, I have here sigma y x at x plus delta x by 2. Okay. So, that is the first term here. Okay. And the second term has 2 negative signs here. It has 2 negative signs here. So, this becomes plus sigma y x at x minus delta x by 2, okay, and there is a common factor of delta x, delta y, delta z, okay, divided by 2, okay, plus, okay, these last two terms, which is minus sigma x y at y plus delta y by 2 plus minus sigma x y at y minus delta y by 2, okay, that is these two terms, okay, these two terms, okay, once again multiplied by here delta x, delta z and delta y by 2, okay. So, that is the torque balance equation, the angular momentum balance equation for this particular differential volume for the angular momentum around the z axis. Okay. And you can see that these delta x, delta y, delta z, they all cancel. Okay. We are taking the limit of delta x, delta y, delta z going to 0. Okay. In the limit as delta x, delta y, delta z going to 0, you can see this goes as delta x square and delta y square. Okay. So, in the limit as it goes to 0, this entire left side will go to 0. Okay. The entire left side will go to 0, and okay, on the right side I have sigma y x at x plus delta x by 2 plus sigma y x at x minus delta x by 2, which I can write approximately as 2 sigma y x, okay, at x y, okay, minus 2 sigma x y at x y is equal to 0, okay, because the left side is essentially 0 because it goes as delta x square and delta y square. Okay. So, based upon this momentum conservation equation, you can basically infer that sigma x y is equal to sigma y x. This is based upon angular momentum conservation in z direction. Okay. Similarly, you can do angular momentum conservation in x direction and angular momentum conservation in y direction. If you do it in x direction, you will get sigma z x is equal to sigma y z is equal to sigma z y. This is angular momentum in x direction, and similarly sigma z x is equal to sigma x z, angular momentum in y direction. Okay. So, based upon angular momentum conservation, you get an important result here for the stress tensor. Recall that I had written sigma is equal to E x, E y, E z. And I showed you that these off diagonal terms are both equal, sigma y x is equal to sigma x y, sigma x z is equal to sigma z x, and sigma z y is equal to sigma y z. What that implies, okay, I should write the other unit vectors here. What that implies is that in order to satisfy angular momentum conservation, the stress tensor has to be symmetric. Okay. So, the stress tensor has to be symmetric in order to satisfy angular momentum conservation equation. Okay. Okay. So, I have told you a few things about the stress tensor. I have related that to the force acting at a surface. Okay. I have talked about the force acting at a surface and related that to the stress tensor, that is sigma dot n is the force acting at a surface whose outward unit normal is n. Okay. the force is sigma dot n times delta s. I have showed you how to decompose it into components, the normal and the tangential components. Normal component along the perpendicular to the surface, tangential component in the plane of the surface. Okay. And I have derived angular momentum balance equation for you to show you that the stress tensor has to be symmetric. So, we will complete a further discussion of the stress tensor in the next lecture before we go to what is called the rate of deformation tensor. Recall that the constitutive relation for the mass flux relates the mass flux to the gradient in the concentration. Heat flux relates the heat flux to the gradient in the temperature. The equivalent for the momentum flux should relate the momentum flux to the gradient in the velocity or the gradient in the momentum density. Okay, the momentum density is the mass density times the velocity. So, we will analyze the gradient in the velocity in the next class and then relate the derive the constitutive relation relating the stress to the gradient in the velocity. We will continue this in the next lecture. I will see you then.